시작하겠습니다. 제가 끼어드는 거 안 하려고 했는데 자꾸 끼어들어야 되는 상황이에요, 지금. 일단 우리 라이프 사이클 코스트는 정확하게는 내일 하는 캐틀락에서 하는 겁니다. 지금 여기 오퍼스 10에서 얘기하는 이 비용 모델에 관련된 거 only 여기 적혀 있는 것만 여기서 계산을 해주는 겁니다. 기타 라이프 사이클에 관련된 일반적인 비용을 산출하는 방법들에 대해서는 아마 캐틀락에서 정확하게 코스트 브레이크다운 스트럭처가 정의가 되고 거기에 맞게 이제 비용을 산정을 하는 거지 여기서 실제로 하는 거는 일단 아니라는 거. 그 다음에 뭐 아무튼 이런 그림들이 쫙 나오죠. 그 오퍼스 10에서 이제 주요 계산하는 내용들은 대개의 경우 스페어에 관련된 투자 비용만 주로 산출돼요. 그 다음에 스페어하고 직접적인 연관이 있는 메인터넌스에 관련된 비용 주로 이제 그것들만 산정을 하는 거고 혹시 나중에 라이프 사이클 코스트를 위해서 우리가 이자율이라는 걸 줘야 됩니다. 왜 그러냐면 시간의 흐름에 따라서 돈이라는 게 가치가 틀려지니까 그래서 만약에 오퍼스 10에다 이자율을 주게 되면 뭐가 다시 계산이 되냐면 감가상각비, depreciation value라는 게 아까 나왔었죠. 그 다음에 그럴 일은 거의 없지만 우리나라 무기체계에서 아까 salvage value 해가지고 그런 얘기 했었죠. 잔존 가치 뭐 이런 것들까지 만약에 계산을 해야 된다면 반드시 선행 조건이 뭐다? 이자율이 디파인이 돼야 된다. 그래야지 계산할 거 아니에요. 그게 정의가 안 되면 계산이 안 되는 겁니다. 그래서 여기서 기본적인 계산을 한 다음에 이제 LCC 모델로 이렇게 넘어가는 거지 한꺼번에 그냥 뭐든지 다 코스트가 계산되고 그러면 우리가 사실은 할 일이 없어지죠. 어쨌든 그런 것들이 여기서 선행이 돼서 저쪽으로 넘어가야 됩니다. 그 다음에 시간에 따라서 변하는 것들은 여기서는 고정비, 리커링 코스트 두 가지만 계산을 했잖아요. 만약에 시간에 따라서 변해가면 그거는 시뮬레이션 결과에 따라서 비용은 다시 집계를 할 수 있도록 심록스에서 정의가 될 겁니다. 그런 내용들. 그래서 비용 계산하는 거에 대해서 특히 코스트에 대해서 오퍼스 10에서 할 수 있는 한계 그거만 여기 슬라이드에 나와 있다. 그 정도만 일단 이해를 하시면 혹시 다른 것들하고 오해가 없으실 거라고 생각이 됩니다. LCC하고 틀린 겁니다. 여기 나와 있는 건 LCC 아니에요. 여기서는 단순하게 그냥 고정 투자비하고 반복적으로 발생되는 어떤 코스트에 대해서 간단하게 일단 산정하는 거다 이렇게 생각하시면 됩니다. 이렇게 마지막입니다 이제.
So we're in CATLOC. And so this is then how we interpret it. This is all calculated from OPUS 10. This comes out from OPUS 10, and we get the idea on how we can see and slice the life support costs. And of course, we have only chosen to incorporate these elements. If we put in more costs in our OPUS model, the model will be more detailed, more costs will be displayed. Now, if I want to model using the depreciation concept here and the cost of ownership, I have to go to the global parameters table and I can set the technical life length. Here, what I talked about. This is the scenario length, this is the technical life length. I could also set the interest rate here. So all these parameters are set on the global parameters level. I could also go to my items table and set technical life length per item. So I have different technical life lengths for different items. And if I think we can do that for resources too. But in this case, you can see here that the total cost is the same because we are looking at the life support cost. If I'm looking at the LSCD, I can see that this curve with the cost of ownership is cheaper than the other one. And why is that? This is because in this case, I'm calculating with technical life length 20 years. That means that when the scenario is over, I have not consumed the whole value of my investment. So therefore, it is a more cost advantageous solution. If I check this in CATLOC, I can also see here that the cost is less for my for the case where I could calculate with depreciation cost and cost of ownership. And this is best illustrated if I look in the time dimension. And if I split this up, you can see that my investment cost is spread out over each year instead of having it the first year. And if I look at it from a different perspective here, from the total investment, we say that this is if we want to see the cash flow, so to speak, when the money is spent. We see that it is spent on a first year, but if we look at it from a ownership perspective, the cost is much more distributed over each year instead of the first year. So this gives us a better understand of, do we want to look at the cash flow or do we want to look at the actual costs? So, any questions on the cost model? Okay, then I will try to just summarize a bit here of what we have done in the two first blocks, because actually this was the end of the third block with cost and performance. So what we have done now is actually bringing everything together here and connecting the different entities from the different parts of the picture into the full picture of analyzing the cost effectiveness. We have cost as well here, it's not in the picture. So that's what it's all about. Coming back to what I said in the beginning, to analyze this is the whole system of our logistics support analysis. And finally, I want to conclude this sessions regarding the model here by making some comparisons between OPUS suite model and the S3000L model. Because when we remade the data model a few years ago, we took a lot of inspiration for trying to, because we noticed in earlier versions of OPUS Suite, people who used working with different standards out there were actually trying to convert and modify the data that they had on a different standard than OPUS Suite in order to get the data into OPUS Suite. And once you did that, there was a difficulty to have this comparison between the source data and the model data in OPUS Suite. So we thought that aligning OPUS Suite with the standards that are widely adopted out there and the standards that are used in LSA format, ILS work, RAM-C work, would benefit both us from a development perspective of new functionality, but mostly you as users, because you can recognize your entities in the OPUS model that you see in your source system. So I put together this comparison just to see how they map to each other. And we can see that we have the notion of product variant and breakdown element in S3000L as well as in OPUS Suite now. We have this notion of implementation of hardware part, it's called in S3000L. And we have a product breakdown called the breakdown element structure in S3000L, hardware element part realization, etc. Item structure, part as designed parts list. So it's really possible to map these two together now. And the same if you look at what we call events. Events and justifications are they called in S3000L. We have also the concept of task requirement that calls for a task to do, which need resources. In S3000L, we also have this candidate item, LSA candidate and candidate item analysis to understand which hardware parts and hardware elements that are subjected for maintenance and that should be analyzed linked to a failure mode and should be analyzed and linked to some maintenance tasks. We have failure mode, PM plan is this candidate item activity, which is a justification for maintenance. Scheduled maintenance requires that. So I was quite relieved when I saw this and happy to see that now it is the principal building blocks from widely adopted standards can be found now in OPUS Suite also. And we will have more transparency between the different formats. So that concludes this second part of the first part of building a model, basic model, looking at the cost and performance. So before jumping to the last part for today, which is extending the model, I just want to check if there are any further questions on what we have talked about so far today.
질문하실 거 있으세요?
Otherwise, you're welcome to come up with a question at any time. Now we will talk about preventive maintenance or scheduled maintenance or what we choose to call it. So what is preventive maintenance? Well, it's also called planned or scheduled. Typically a result from FMICA RCM analysis where you have found the justification for implementing maintenance regime in order to prevent failures. And you can often see that this is prescribed by the manufacturer and occurs with a certain scheduled regularity. Now, discipline of itself, when we talk about scheduled maintenance and prescribed by the manufacturer, and in this process of FMEK RCM is to find out when and how often should preventive maintenance be made. Because against preventive maintenance, you have something that is a potential failure that you would like to avoid. But if you are too careful, you might find yourself conducting preventive maintenance with a very high frequency, which will incur more downtime and costs than actual failures. So it depends on the criticality of the function that you want to prevent from failing, but also on cost effectiveness here. Some types of preventive maintenance could be pre or post-mission activities, turnaround activities, inspection and checks, on-system maintenance, component maintenance. Typically, inspection and checks does not require spare parts. It might induce downtime, of course, and it requires resources. On-system maintenance might require spare parts, depends. Induces downtime, of course, and requires resources. Component maintenance does require spare parts. Induces downtime. How much? It depends on the item stock. How much do you have in to replace the items to be maintained? And it requires resources. Scheduled preventive maintenance is characterized by its occurrences with a regular interval. Can be calendar-based, says that regardless of how much the system operates, it should be subjected for maintenance each 1,000th hour. It can be operational-based, which is quite common the case. Irregular time intervals, because it depends on how much the system is used. Each system has a counter that can say how much it's used, and when the counter ticks in for the maintenance, the system is taken out for maintenance. Here you can also use other counters as flight hours, kilometers, rounds, fire, takes off and landings, etc. Of course, does preventive maintenance induce downtime? And this is also what we mean when we say mean time to maintain, mean time between maintenance. So this is the collective word for all the maintenance, corrective and scheduled, that can be imposed on the system. But it is also interesting from a spare part perspective, because in a world of spare part calculations and optimization, this is also something that will impact the stock levels and how much we need in stock. So spare part, we have two types of demands. We have failures and we have preventive maintenance. And they are normally served from the same stock location. But they can have different resupply time. Depends on what you are repairing. An item might take another time, different duration than maintaining the item. And the demand frequency could be different from the failures as well as from the scheduled maintenance. But in the world they are served, our world, they are served from the same stock. So we need to take this into account when we dimension the stock. And thus it has an impact on spare part optimization. And as we have concluded also that preventive maintenance impacts the availability. Preventive maintenance in OPUS Suite. We are assigning the preventive maintenance, we create a preventive maintenance plan to which we link, as we saw in the beginning with the events, we link this preventive maintenance plan to an item, a breakdown element, or a combination of breakdown element and item, or to the variant itself on system maintenance. But anyway, we can also tell them the interval, what is the operating time, what is the component affected, and of course, what actions are to be carried out during the preventive maintenance. We talked about this before, how we shape how we build up tasks and task packages. Characterizing task and task packages that they are they can only be assigned to one component in the OPUS model. Then we could, as we saw before, build up maintenance activities. And they can be assigned to handle different components. So typically during a scheduled maintenance activity, you might want to replace several items at the same time. And therefore you need to define a maintenance activity for a preventive maintenance activity in OPUS 10. Then you have to build up your schedule. You can say that a certain maintenance is occurring according to a certain interval, in this case once a year. So the cycle is annual, one sequence, interval each year that repeats itself. But you could also have a maintenance cycle that is not the same every year, but is consisting of various activities. So let's say, for example, that you have one activity that is a small overhaul of an engine that needs to be taken place every 100 hours. Then you have a medium activity that is taking place every 300 hours. And then you have a large overhaul activity that's taking place every 600 hours. And typically, in this sequence then consists of 6 steps. It's one step every 100 hours, but you will do different things. So you need to define this sequence of 6 steps. Typically, when you conduct the medium activity, it consists of the small as well. So you don't have to do the small first and then the medium. And typically the large activity might consist of both the medium and the small. So you don't have to do small, medium, and large. And this is a very good feature that you can implement in the OPUS 10 model in order to make this more realistic. So you can build up long chains of maintenance activities that are attributed to various parts of your systems. So let's have a look in the tool how this is built up. So we have our famous model here now, which we are fairly familiar with at this time. We can see here that we have a new category of tables that is applied here, which is called PM. And the tables PM plan, PM interval, and PM schedule. We also have two new tables here under maintenance, which is called maintenance activity and maintenance activity content. But let's take everything in order first. So you start with defining the PM plan. So we have two different preventive maintenance plans here. One PM plan on the engine, on this component, and one that applies to the product variant itself here. If we look at the PM plan, start with the simple one, the annual check of the system, of the product variant. We have only one row here defined, happens once a year, regardless of utilization. The interval 8,760 hours. So this PM plan consists only of one sequence that is repeating itself. So from defining it in the PM plan to given the interval in the PM interval table, and then assigning what is it that we are going to do. So I have defined maintenance activity here that's called maintenance activity vehicle A. Now this maintenance activity vehicle A is consisting of two tasks. One is, of course, overhaul of the vehicle. This has nothing to do with any spare parts. And then we are replacing the drain valve, this component that is sitting down here, reordering it. During this maintenance activity, we are removing it, throwing it away, and putting in a new one. That's always happening. You can see that it's green. That is probably because it is also repaired sometimes when it fails. But during the maintenance activity, we throw it away. And here we also have a probability that we could assign to a certain task. So we can say that, okay, maybe we are not throwing it away every time. If I put 0.7 there, I could say 70% of the cases we throw it away, and 30% we leave it. Now this task, overhaul vehicle, this is a task in this case. And you remember that you must define tasks to build up the maintenance activity. So I have to define this task in my task table. This is the table where you have all the tasks definition, and here you have the overall vehicle task. It's done on the maintenance level 1, that means on operating level. let's look at the next maintenance activity, that PM, preventive maintenance plan that we have. That is the PM plan for the engine. This is slightly more complicated. We have a 10-step plan. The maintenance takes place every 500 operating hour. And we have a cycle of 10 steps. So it's not the same that will be occurring every year. And this is described in the maintenance schedule table here. So here we can see that we have the first 4 times we do maintenance activity engine minor. Then we have a maintenance activity engine intermediate, followed again by 4 minor, and then it's time for a major. Then it restarts again with 4 minor, intermediate, 4 minor, major. So this is the cycle. And what's good also when you put this preventive maintenance plan on the engine, on the hardware item here, is that if we have multiple engines in the system, this will be taken care of automatically during the calculation and optimization, that we have that it will take into account that we have multiple of this item. So we will get the volumes of the maintenance adjusted according to the number installed. If we go to the maintenance activity, we have now 3 maintenance activities defined for the engine. The engine minor, the intermediate, and the major. And we describe them. Minor consists only of 1 task, overhaul engine. This is what we do 4 times, 4 years, or not 4 years. First time, 4 times we reach 500 operating hours. Then we have the maintenance activity intermediate, which consists of 2 tasks. First of all, the overhaul engine intermediate, which is a separate task, and the rectify engine module. And this is then specified on engine module 4. And you remember what I said, that a maintenance activity can be conducted on multiple components, where a task is just assigned for 1 component. So here we have both the engine and the engine module are maintained during the same activity. These tasks are as well defined here. We have rectify engine module here, and we also have the overhaul engine intermediate here. It takes 24 hours and requires maintenance level 2. And finally, we have the maintenance activity major, which consists of the overhaul task major and the rectifying engine module 4 and 3. So here we have 3 components involved in the major activity. So this is the way that you build up your preventive maintenance regime for your product. We make a calculation. We get our curve, which we don't have to explain more now. We talked about it the last time. But if we go behind the scenes and look at we want to check some preventive maintenance volumes here. Task or PM per station, or we can say system, an item. We can see here the PM plan carried out on what vehicle, what component, and how many actions per year this occurs. And of course, the ones that were this activity that occurred every calendar year, it's quite predictable. 1 time per system per year, so it will be the exact same amount of number of systems deployed at the various bases here, 12, 4, 4, 4. But the ones that are carried out based on operating time is, of course, depending on the operational profile. So we see that we get a bit different volumes here on that. This gives us an idea of how much maintenance volumes we get. We can look also, we can see here, for example, that the drain wall is consumed 24 drain walls per year, which is also according to expectation. 12 plus 4 plus 4 plus 4 becomes 24. What we did, we replaced the drain wall during the variant activity. So this will require us to buy 24 new drain walls every year. Has to be taken into account in the cost calculation. And if we look at then the reliability system here, we can see that we have some different results now in terms of reliability. We have the mean operating time between maintenance, which comprises all maintenance. Then we can see that we have mean time between failure, which is one value for the system. And we have mean operating time between preventive maintenance. And these two weighted together will give us a total mean time, operating time between maintenance of 101. So we can see exactly how much is derived from each type of maintenance activity. Of course, we can link costs to this as well. So, and we don't explicitly link any costs to the PM activities because we are using the same tasks in the at the bottom of this maintenance. It is still tasks that we are using here. And it could be, we could reuse the same tasks for repair activities, for preventive maintenance activities. So if we assign some costs here to our various tasks as we had before, and also to our overhaul activities, they are a little more expensive. We make a calculation here now. We have done so. Let's bring in the result in CATLOC. You see I started a new CATLOC model. I choose build OPUS suite cost model. I have already done the built-in OPUS suite cost model in CATLOC. I want to insert the OPUS suite link so that I can link directly to the result from my OPUS model. And let's choose automatically the point of availability, 90%. Saving PM, cost analysis PM. Oh, I will have to remove the other ones so we're not cluttering the pictures too much. And this is not calculated with depreciation cost, we take the regular cost. We can now see that we have life support costs as expected, but we also have the recurring cost of preventive maintenance here. together with corrective maintenance and the other ones that we have, and the item consumption cost because of the drain wall. So if we want to see how the maintenance cost, the preventive maintenance cost is distributed, this is the annual cost for preventive maintenance, but we want maybe to see on the material how it's distributed. We can see that the vehicle A is the most expensive from a preventive maintenance perspective, followed by the engine. And then you can see here that the engine module 4 and engine module 3 are quite low cost carrying of the preventive maintenance cost. And if we want to switch view and look at the item consumption cost here instead, we see that we only have one item that is consumed, and this is the drain valve, which was as expected because we don't have any other items that are reordered. And these are the total costs over all materials. So this gives us a good understanding of the spread of the total cost, and now also together with preventive maintenance. Now, one thing that's difficult to take into account into a model like OPUS 10 that we have is the positive effects of preventive maintenance. How do we know how many failures do we avoid because of doing preventive maintenance? This is not an exact science, so you can't really say that this is, if we do preventive maintenance on this item, failure rate will decrease with this much. But there are some models for how that can be done, and I know that we are investigating on how that could be incorporated into OPUS 10, because that's certainly something that you would like to assess. But as you imagine, it's a bit complicated to really assess it. You want to prevent the failure, but how much failure you prevented is difficult to say because you never know when the failure actually would have occurred. So it's a discipline of itself to analyze that. Questions on preventive maintenance? Does it make sense? Does it relate to how you are used to see preventive maintenance?
In the item consumption cost means unit price.
Yes. But you could imagine something else if you would like to, because you have reorder price factor here, and that allows you to adjust the price in time if there is some extra fees to be incurred just for the reorder, etc. And this is also optimized. The stock level for the drain valve here now is optimized. So if we have this case again, we can see here that we, in OPUS, we can see the, let me see here, the stock level of the drain valve. We see here that we should have 4 of them at the central base and 1 on the main base and 1 on the regional to reach this point, 91% availability. But also this case, since we are performing reorders, we also get reorder item station here for the drain valve that gives us, okay, the stock size is 4. Since we are reordering to the central, reorder size is 3, and we need to place the reorder when we are at 1 in stock level. So this is also optimized results coming out of OPUS 10, reorder policy. And that could be different depending on where on the curve you are locating yourself.
It means that the reorder point to low down the level 1, we order 2, and level 4.
Yes.
Yes, it's S minus the 3 policy. Yes.
Exactly. One thing also worth to point out when working with a model like OPUS 10 and preventive maintenance is that, as you know, everything is calculated as an average. OPUS 10 will also calculate that there is an average amount of preventive maintenance occurring each year. But imagine that you have a fleet of 10 brand new systems that have an overhaul interval that's going to take place after 7 years. And in your OPUS model, you are looking at the horizon of 5 first years. Should you include the preventive maintenance of the 7-year overhaul in your model or not? I would not, because they won't occur during these 5 years, since you have the overhaul at year 7. But if you write in the OPUS model that you want to have an overhaul the 7th year, it will calculate an average of, okay, it will say that 1.2 systems will be in maintenance on the average every year, which might be true if you have a fleet that is big enough with very evenly spread, that is big enough to have enough individuals that have been used with different time. So you have the age of the fleet is very spread out. In that case, it would be realistic to think that on the average, one system will be in maintenance every year. 1.2 system will be in maintenance every year. But if you have a brand new fleet, probably no one will reach this maintenance during these 5 years. And then you should not include the maintenance in your scenario. This is also much clearer in SIMLOX because then we can see exactly when the maintenance actually is occurring. But OPUS is calculating with average number of systems in maintenance every year, and therefore you need to pay attention to a thing like that. I don't want to complicate it too much right now, but that's an important part of the OPUS model and the preventive maintenance to consider. So now we extended the model with preventive maintenance. Let's continue to extend the model with maintenance resources as well. Maintenance resources, I show you this picture again, they can be of a very maintenance, these are the elements of support. And maintenance resources are typically tools, equipment, facilities that are required to perform maintenance. So far in our model, we have no resources at all. We assume that all maintenance can take place without resources. And you have, of course, tools and equipment that needs to be used, and also labor, technicians, etc. And consumables, nuts and bolts and oil, grease, lubricants, that over a lifetime will incur quite a lot of costs. Specifically, if you have expensive system that requires specific consumables, that could be a substantial amount of money. So how we make use of resources? Well, first of all, we must define them. What are the resources? What do they cost? And how much are they available and can be used? We have a task that also can cost money and take some duration. And we need to connect these two to say that these resources are required to perform this task. Now here we need also to pay attention because by default the resource is considered to be used the whole task duration. So if you are including in your task duration administrative delay, turnaround time, etc., which is not on task time, the cost for the resource will be for all that turnaround time. Therefore, we have separated the task duration with administrative delay, which we have not talked about so far. But just so that you know, that when connecting resources to the task, the resource is assumed to be used the whole task, so we must make sure that the duration of the task is in accordance with the usage of the resource. Then we have consumables. They cost money and are given in a certain unit of measure. Again, the task comes into play and we link the consumable together with the task and we tell how much of the consumable is used for this task. So, let me see if I have that also in the model. I'll start with the resource. Here we have some investment to establish regional depot and investment to establish main base storage. So these are two resources that are not required for any tasks, but we want to put them into from a cost perspective in order to understand that we have resource investments to do. They cost a unit price and then have an annual sustainment cost. Then we also have a technician, or we define a resource that is a technician. We might have many of them. That costs 20,000 per year salary, I can imagine. We need to allocate these resources in our organization. So we say that we have one quantity of the main base storage at the main base and one on the regional depot, and then we have technician, one at each base here. Now, as you see here, maintenance resources are not optimized in this scenario. We give exactly how many they are and where they are. If you were to perform what we call a LoRa analysis, level of repair analysis, we would optimize both resources and spare parts together in order to understand what is the best location for the maintenance to take place. This is another extension of the OPUS model and a quite powerful capability of OPUS 10 to perform a LoRa analysis. But this is out of the scope for this training session, but something to keep in mind.
If there are some test tools, the cost may be included in the regional or main base.
Mm-hmm.
You already classify the technician cost differently.
Yeah.
If you need other tools or facilities, it must be included in the regional or main base.
Yes, you could do that.
Yeah, it's very simple.
Yeah.
Yes.
So you can define how many resources you would like here. But if you want to connect them to the usage of maintenance activities, we have then the table called task resource, where I connect the technician to replace primary here. And I say how many technicians are required to perform the task. And I will remove the thing also. And also resource probability, I think it's to say there is a chance that the resource is not available. In simulation, in SIMLOX, you can describe detailed shift schedule for the resources when they are available and when they are not. So for example, most technicians do not work 24/7. They work 8 times a day, Monday to Friday, then they are off on Saturday, Sunday. So of course that impacts the downtime of the system that you don't have. Or should you maybe have night shifts with people coming in? So you can play a lot of that with that in SIMLOX. But not here. I'll make a calculation again. Here, resource modeling. And what kind of results do we have for resources? Resource volumes, resource quantities. We can see here the resources available. We have 4 technicians. Average number of resources in use, only 5% of the time. That's not much. And the distribution of the resources as well. But we can now also include the resource cost in our CATLOC analysis. So if I just switch here, result file for CATLOC, make calculation, we have resource sustainment costs here now as well in our cost model, because we have this annual cost per year. And we could also add in the OPUS model here something called, where did we have the man-hour costs? That was something we had before, I think. Yes, resource usage hourly cost. So say it costs $50 an hour. Now we have, if we look at the resource perspective, we can see that technician costs this much. We can also see if we break down the corrective maintenance costs. We can now see that we have system cost, resource costs for the corrective maintenance as well here. So we're gradually building out our cost model as well. So this was a quick glance at how to build resources. Now we should look if we want to incorporate consumables as well. I will see if I had built that one based on the resource case or not. Yes, we already have the resources here. And then we have 2 new tables, consumable, lubricant, that costs 100. And replace gearbox, we need a quantity of 2. So let's say lubricant 2 liters. That means that task consumable, we need 2 liters to when we do the replace gearbox module here. I get again a new OPUS 10 curve, and we shall look at the costs in CATLOC, which is much more convenient. And let's check corrective maintenance costs here. We have, this was from preventive maintenance, so we have costs for consumables here as well, included in the model. And from a result perspective here, it's quite interesting as well to see in OPUS 10, because we can get a dimensioning dimensioning of consumables over the support period, the support cost period as well. So you can see here, volumes of consumables, lubricant, 5.57 liters per year, which will give us this cost per year, and how it's distributed over, this task was only carried out at the central location, so that is where the cost is incurred. And this is quite good, I think, because when you have, for example, replace parts on aircrafts, sometimes you never put back a bolt that you have taken out. You always replace with new bolts. And that is, every time you have this maintenance task, you consume the bolts. And over many years, that could be quite large volumes. So I think by including this in the total life support cost analysis is quite important to get the correct cost. Any questions on consumables? Yes.
In OPUS 10, we define P and preventive methods, but in CATLOC, how calculate C and C? That I think preventive maintenance cost, but we define P and just P and P. So how calculate in CATLOC C?
The corrective maintenance cost. It's based on the number of repair volumes conducted, because we can see it's based on the result from OPUS 10. So we can see, for example, we have corrective maintenance, repair volume system. We can see how many repair actions on the system we did per year. But we can also see how many repair actions per item we did per year. And based on that, in the CATLOC model then, if we look at recurring costs, there we go here, recurring costs, corrective maintenance costs is divided on upon repair item corrective maintenance cost, for example. We can see how this is calculated by the formula here. So we have an expression that says multiply the mean repair quantity with the repair rate and the price per maintenance task. So it uses these parameters here, some of them which is defined in CATLOC, some of them which are read from the OPUS result file. And then we get a value of the corrective maintenance costs. And we can check them here on in the value grid as well. And we can collapse some of over the total domain here. Or so I thought. Maybe that was not the right cost element. Anyway, this is how it's built up in CATLOC. So we have expressions that take result parameters coming out, the repair rate, for example, and the mean repair cost, and together they form the expression to calculate the cost. But you have also the cost directly in OPUS, so you could take the explicit value directly from OPUS as well. Is that an answer to your question?
혹시 질문이 왜 프리벤티브 메인터넌스만 얘기하고 커렉티브 메인터넌스는 얘기 안 하는 거? OPUS 10에서는 PM 행위만 정의를 한 것 같은데 카탈로그에서는 계획 정비 외 비용도 계산이 원래 정비는 계획 정비, 비계획 정비 있는데 스페시피케이션에서는 비계획 정비는 그냥 리페어로 그러니까 둘 다 얘기한 거예요. Yeah, his point was that why do not present about the corrective maintenance, but in your presentation you say repair instead of corrective maintenance.
Aha.
Yes.
Okay, that's the same thing.
Yes, same thing.
Yeah, repair.
You don't emphasize the corrective maintenance.
No. But it's good that you ask because I use sometimes these expressions and names for things a bit lightweighted because I'm used to it, but it's not evident that corrective maintenance and repair is necessarily the same. So it's good that you ask. So this was actually the end of the scheduled topics. So what did we learn today then? We kicked off today by talking a bit about analytic lifecycle management and OPUS Suite's role in supporting analytic lifecycle management and the importance of allowing yourself to get the good decision support foundations for your decision. We went into the details and built a basic model, learned the building blocks of a basic OPUS Suite model and how you build up the model. We spent some time on understanding and interpreting the results as well as costs in OPUS 10 and how to interpret those. And finally now we did some first steps to expand the model with introducing preventive maintenance and resources. But of course, this is just scratching the surface. We have a lot more that we could explore. We have, to give you some examples, endurance modeling, when you, for example, want to assess the capability of performing of your readiness when you are cut off from your regular lines of supply in a deployed situation. We have LoRa XT, which stands for extended LoRa because it's not only level of repair analysis that we're talking about location of repair analysis here. We have FBD modeling, fleet buildup, phased scenario, we had some interest for that as well, how you are ramping up the fleet buildup. Complex configurations, how you maintain multiple product variants in the same model with the different choices of contract optimization, how you can optimize the performance on different locations, not to maximize the overall performance, but if you are a supplier and you want to not to overinvest in support solution, but you want to target the optimized, the contracted performance, which could be different on different locations. So we have that capability in OPUS 10 as well. Self-supported deployments, very suitable for large ships that are out at sea for many months, and they will take care of, they need to think a bit differently when you are away from shore and needs to be self-supporting during these missions. And of course a lot of more functionality. So with that, I know that we are a little bit early, so I don't know how you feel. Young?
야, 이거 하나 더 있어가지고 계속 할까요? 아니면 오늘은 여기서 쓰고 내일 좀 확실히 할까요? 너희가 편하겠어요.
뭐예요?
그래요? 일단 오늘 한 거 정리 글쎄 막 정신없이 시간이 지나가요.
잘했어요.
네, 네. 요 네 꼭지를 이해하시겠어요? 이런 식으로 하면 되겠다. 사실은 아주 기본적인 모델만 아까 그 세 꼭지가 있었죠. 오퍼레이션, 시스템, 그다음에 하나가 서포트. 이 세 꼭지를 어떻게 모델링하면서 믹스를 해야 되는지에 대해서 오늘 얘기를 하는 건데 주로 요 네 가지 토픽까지로 얘기가 진행이 되고 로라 익스텐션 같은 경우는 많이 물어보는 모델이긴 합니다. 특히 이제 리소스하고 로케이션을 최적화를 해야 되니까 아까 얘기했던 로케이션에 들어가서 이제 확장 모델이다 이렇게 얘기를 했는데 저쪽은 많이 하죠 실제로 공시적 분석할 때. 저쪽 모델 인듀런스라는 개념은 그 지원 측의 구조가 없어져 버렸어요. 파괴가 됐을 때 비교를 굳이 하자면 지금 여태까지 얘기한 건 전시라고 생각하면 되고 아니 평시라고 생각하면 되고 인듀런스라는 개념을 적용하면 이제 뭐 전시 이런 거 확장할 수 있다 이런 뜻입니다. 예상하는 거. 나머지 저 시스템이 이제 컨피그레이션이나 기타 쭉 해가지고 이런 내용들이 되는데 아마 요것들은 안 하는 거죠. 내일 이제 신속수 해야 되니까. 그래서 이쪽 부분에 대한 내용이 혹시 더 필요하거나 궁금한 게 있으면 지금 질문을 해도 될 것 같아요. 제가 봤을 때 얘기하시면 되고. 예, 아무튼 이거보다 훨씬 더 많은 모델링이 가능합니다. 실제로 그것만 해도 아마 한 5일, 2주일 이렇게 교육을 하면서 가능하다 이 정도까지 하고. 요 더 해야 될 거에 대해서 혹시 뭐 질문할 게 있으면 질문하셔도 됩니다. 아니 뭐 개인적으로 따로 이렇게 박사님 계속 하시고 싶으세요?
저는 개인적으로는 오늘 진도 더 나가고 내일 일찍 끝나는 게 좋으니까.
민주주의 원칙에서 손들었어. 더 하자. 제가 교통학자로 오늘 전부 다 지치신 것 같으니까 좀 이게 학습이 돼야지 내일 또 할 수 있을 거거든요. 오늘 이렇게 학습한다 이렇게 생각하시면 오늘 여기서 수업하고 내일은 조금 더 빨리빨리 이렇게 하는 걸로 하겠습니다. 중간에 좀 끼는 거 빼도 돼요. 저기에서 생각하게 하시면 되죠. 혹시 뭐 다른 거 질문 없으세요? 수고하셨습니다. 일단 수고하셨습니다. 땡큐.
Thank you very much. I had a very exciting day today. Looking forward to tomorrow as well. Many good questions coming up, so make sure to get some good sleep tonight and be prepared.
Thank you for your lecture. I have just two questions. Yeah. The first one is the system performance metric.
System performance metric. Yeah.
Yeah. You explain availability just A. Yeah, what does it represent? Available is operational or material?
Operational availability.
Just okay.
It will say the probability that the system is available when you need it.
But I know in DoD guidebook, the RAMC and PBL is first level performance is material availability. Yeah, but this OPUS suite doesn't calculation.
It doesn't make a distinction between material availability and operational availability. And I think that, if I remember correctly, material availability, that is the whole support concept with everything.
Yeah, but I know the vital difference between that is I know the maintenance plot. Yeah, is maintenance plot exists. That is we calculate material availability, but it doesn't exist the maintenance plot. AO is equal to AM. I know that. Yeah, so in this OPUS suite is not input parameter is doesn't include the maintenance plot in input parameter.
No, I'm not sure what you mean with maintenance plot.
Yeah.
What is that exactly?
You don't know maintenance plot? You don't know about that?
I mean, I probably know, but I don't know the notion maintenance plot. What is that? Is it?
It's it's a maintenance strategy about some OP operational site some product is failed, then the maintenance shop is immediately supply that end item, and the readiness operational readiness is immediately.
Okay.
Yeah. That is.
Isn't that comprised in the whole picture? You think?